Hello everyone, I'm Dr. Moin. In this video we are going to discuss about evolved gas analysis. We have seen earlier various thermal methods of analysis, and we have seen that at different intervals different gases are evolved. Sometimes we might be interested to know the nature of these gases. So these things are performed in this technique which is called evolved gas analysis. And this is part 2, in which we will discuss the spectroscopic methods. In part 1, we have seen the basic principle of evolved gas analysis, its instrumentation, and various physical and chemical methods for the analysis of evolved gases. So if you didn't watch that video, then I am putting the link of that video in the top right corner, so you can also watch that first. Before starting the video, if you didn't subscribe my channel yet, then subscribe it right now, and also press the bell icon so you may get in touch with my upcoming videos. And here are the contents of current video. We will see in detail TGMS, that is thermogravimetry mass spectrometry. And we will understand this technique TGMS with the help of different compounds, their spectra, like calcium oxalate monohydrate. Then we'll see the spectra for polyethylene oxide, and then we'll see the example of brick clays. So let's get started. So first of all, mass spectrometry and simultaneous TGMS. Mass spectrometry is a very good technique for identification of evolved gases and vapors. If a sample in vapor state is introduced into the mass spectrometer under high vacuum, usually better than 10⁻⁵ torr, the molecules M may then be ionized in various ways. So first of all, the sample is introduced into spectrometer in the form of vapor state, and it is introduced in the area which is under high vacuum, where the pressure is below 10⁻⁵ torr. Then these molecules are made to be ionized by using different ways. For example, by high energy electron impact, using electrons accelerated by a potential difference of about 70 volt. So one of the method for ionization is the use of high energy electron beam. So high energy electron beam is made to fall on these molecules. So what happened over there? So these are the molecules of sample, and these are high energy electrons. So it is made to fall on this molecule. So it is highly energetic enough to eject a single electron from this molecule, and that is converted into cation, and that electron is added over here. So 2 electrons are here. The species, this is M positive ion, that is cation. Actually it is the molecular ion, and generally a radical cation with an odd electrons. With such a high energy, there is a high probability that the molecular ion may fragment into lower mass fragment ion and a neutral fragment. So because the electron beam that carries very high energy, so these molecular ion may be broken down into component fragments, and these fragments may be in the form of ion, and they may also be the neutral fragments. For example, a molecular ion of propanone, so here is propanone or acetone, with a mass to charge ratio, and that is 58 in the case of this propanone ion, it readily fragments So it is broken down into the fragments, either to this CH3CO fragmentine with mass to charge ratio of 43, or the other fragment may be the methylene with the mass to charge ratio 15 AMU. 15. The fragmentation pattern is the characteristics of molecule being studied. Means what fragments will be formed there that vary from molecule to molecule. Each molecule has its own fragmentation pattern. The positive ions are accelerated through magnetic and or electric fields. Then these positive ions or fragments which are formed previously, so there are applied electric fields and magnetic fields. So these positive ions are accelerated by the use of these electric and magnetic fields, which separate them according to their mass to charge ratio, and the ions are then detected by an electron multiplier. The mass spectrometer operates in a high vacuum, as we have seen earlier, which sets a problem of interfacing the spectrometer to any thermoanalytical system. And because mass spectrometer operates under a reduced pressure, so this thing make it quite much difficult to make in contact this spectrometer with some thermoanalytical system. The evolved gas is extracted from the thermal analysis instrument through a heated capillary leak at a suitable temperature. So now we are moving towards the evolved gas analysis. So we are studying some thermal technique like TGA, DTA, DSE, whatever is that. So gases are evolved there. So these evolved gases are extracted from that instrument through a heated capillary leak at a suitable temperature. Methods such as jet or orifice separators have been used to reduce the pressure before the mass spectrometer. So there are some suitable methods like jets or orifice separators which are used to reduce the pressure of these gases before they are made to enter into mass spectrometer. The sampling capillary is set as close as possible to the sample and may be heated up to around 250 degrees centigrade. So sampling capillary is kept quite close to the spectrometer and the sample is heated as well around 250 degrees centigrade. A second stage reduction using a fine frit as a molecular leak may be added. So there is another assembly which may be attached with this. This arrangement reduces the transfer time between the TG and the MS to less than 1 second. And this arrangement, by the use of this arrangement, the transfer of gas molecules can be made at a very reduced time, normally in 1 second. And all of these processes is shown in the next slide in the form of a figure. And here is the diagram of TGMS system, which is shown over here. We can see this is TGS system. Here is the furnace, sample pan. So sample is kept in here in sample pan. So heat is provided through the furnace. So gases are evolved which are moved over here through this capillary, which is silica lined stainless steel capillary. And together with there is a heat supply system to 50 degrees centigrade heat temperature is provided. Then there is second stage reduction over here. The vapors are moved in this second stage reduction through this Teflon seal, where is there is also present the rotatory pump, so that the pressure of these vapors can be reduced, and ultimately these vapors are made to enter into the spectrometer. The software available with modern mass spectrometric system, so definitely softwares are also available with the modern instruments. So these allows us to select several mass numbers and monitor them continuously throughout the run. So we may select a range of masses, that up to what mass, in what range we are interested to observe the different fragment ions, or to perform a rapid scan over a range of masses to obtain full mass spectra of gases evolved. So in this way we get a complete mass spectra of the mass range which is supplied by us through the software. With proper materials and pumping, there is little retention of gases in the capillary. So if the system is proper, pumping is proper, so there are no chances of retention of gases in the capillary or in the spectrometer, and hence there are no chances of memory effect, which may cause error in results. So errors in this way can be avoided as well. So let's understand it with an example. So here is an example of calcium oxalate monohydrate, and here on the right there is a TG, DT, DTA, MS curves for calcium oxalate monohydrate. So we can see here different curves. So here we can see here is the thermogravimetric curve. This goes this way. Then differential thermal analysis curve. This is the second curve which is shown over here, and then some other curves which represent the different various gases which are evolved during this process. So the thermogravimetric trace shows 3 steps over the temperature range up to 800 degrees centigrade. So we can see the temperature is going towards 800 degrees centigrade, and there are 3 steps. We can see this is the first step, then is second, and here is the third step. And by examining the evolution of the molecules of water, so what could be the vapors or gases which may be evolved during these 3 steps or processes? So there could be the water vapors with mass to charge ratio 18, or there could be the carbon monoxide with mass to charge ratio 28, and there could be the carbon dioxide with mass to charge ratio 44. So here is 18, 44 and 28. So we can say most certainly what these changes represents. So these are 3 expected evolved vapors or gases through this process. The run was performed in argon environment with mass to charge ratio 40/40, which was subtracted from the spectra as a background. The evolution of water corresponds exactly with the first DTG, that is derivative thermogravimetric peak at 200 degrees centigrade. So this is DTG peak, and we can say this represents the removal of water which is around 200 degrees centigrade. So this peak is due to removal of water vapors through the compound. The evolution of carbon monoxide with the second at 480 degrees centigrade. So this second peak which is at around 480 degrees centigrade, so this represents the evolution of carbon monoxide, and of carbon dioxide with the third around 770 degrees centigrade. So here is the third peak, DTG or DTA peak, which is at 770 degrees centigrade, and this represents the evolution of carbon dioxide. Note that there is also some carbon dioxide at the second stage. If we see these peaks, so this is carbon dioxide, and the real peak is at this position 770, but if we see that some peak is a little peak of carbon dioxide is also appeared at the point of carbon monoxide, that is at the second stage, and this is possibly due to disproportionation of carbon monoxide. And we can also see that mass to charge ratio 28 trace also peaks during the third stage. This one is the peak for carbon monoxide, and this is the real position of this peak, but a little peak of this one also appear at the point of carbon dioxide position 2, and this may be due to the fragmentation of carbon dioxide, that is, the carbon dioxide may be broken into carbon monoxide and atomic oxygen. So that is why a little peak of carbon monoxide is appeared at the position of CO2 peak as well. So next one is an example of polyethylene oxide, and here are the curves for this one. So this is TGMS curves for polyethylene oxides, and the sample is taken from two different suppliers which are shown over as A and B, and these are run in two different conditions. The top curves, these are the top curves, show the TG under air full line. So full line shows TG curve in air, while dash line show in nitrogen, same as the case over here. While these lower curves, these are the mass spectral response curves. So the polymer decompositions may be extremely complex, and many products may be evolved simultaneously. So to study the polymer decomposition, this is a very complex process, because there could be the possibility that a large number of gases could be evolved over there. The TG curves in air show a DTG peak with several overlapping parts. So we can see that here are the peaks, and they are overlapping with each other here and there. Monitoring of the prominent mass spectral peaks at mass to charge ratio 73, we are talking about this and this. So these may be probably due to C3H5O2 type of species, while that of mass to charge ratio 88, so you can see here the peaks with mass to charge ratio 88. So these could be due to paradioxane, that is C4H8O2 type of species. So these show how they are evolved as a function of temperature, so which can clearly be seen over here. Different samples from different suppliers gave very different traces. We can see here are the trace of supplier A, and here are the results from the supplier B, and these are quite different from each other. And performing the experiment in nitrogen also altered the scans. So same sample from two different suppliers, or same sample under different conditions, so results are quite different from each other. So this can be well understood by looking the TGMS curves for polyethylene oxide. And the last example is brick clays. So here on the right side we can see the curves, TGMS curves for an Oxford clays. A sample of an Oxford clay used in the manufacture of common bricks, given the thermogravimetric curve shown in the figure, and heated at 20 Kelvin per minute in the air. So here is the TG curve. We can see with the increase in temperature this way, the mass is going to decrease due to evolution of different gases. So when we perform the analysis of these evolved gases, so here is the TGM, here is the MS curves for the evolved gases. The evolution of water with mass to charge ratio 18 occurs below 200. So this one is for water. So here is the peak we can see below 200. So there is evolution of water, while at 300 degrees centigrade There's the combustion of organic material which produced several volatiles. So at 300, around 300 degrees centigrades, there is the combustion of various organic material which produce several volatile components. Then higher temperature processes involving the reactions of clays. So when temperature is increased further, so there occur different reactions of the components of the clays. So carbonates and pyrites produce the complex patterns of evolution of carbon dioxide with mass to charge ratio 44 and sulfur dioxide with mass to charge ratio 64. So further the gases evolved and the peak was obtained with mass to charge ratio 44, which indicated that it was carbon dioxide, and another gas with the peak with the mass to charge ratio 64 that was obtained, and it showed that sulfur dioxide gas was also evolved through the process. So in this way evolved gas analysis can be performed, and this was all about the spectroscopic method for the evolved gas analysis. So dear students, this was all about current video, but still there are a large number of videos in the pipeline. So to get them in touch with all of those videos, you need to subscribe my channel. So thanks for watching. Thank you very much.